Academy. A famous quotation is there: don't judge each day by the harvest you reap, but by the seeds you plant. Don't think that how much marks you are scoring in exam, but you continue to work consistently. Ultimately, result will come. At the same time, with the hard work, we have to do some systematic, some smart work. The smart and hard work definitely will lead to success. So there is no doubt to analyze our success each day. So children, let us come to our topic. Today's subtopic is combination of resistors. Why do we combine resistors? If you need some desired amount of current, some specific amount of current, we have to combine the resistors, and the combination may be in series, may be in parallel, or may be both in series and parallel. So according to our desire, according to our requirement, we have to go for the combination. For example, we need less current. That means we have to increase our resistance. That means we have to go for series connection. If you want more current, means we have to reduce the resistance. Then we have to go for parallel combination. So according to our requirement, whether it is series or parallel or in a circuit, some resistors will be connected in series and some resistors will be connected in parallel. So let us start with series combination. So I can say that resistors in series. Cell from where we are drawing the current. This is the key. Here is one resistor. Suppose this point is B, this point is C. I can mention this point as D. Listen carefully. So children, in series connections, resistors are connected one after the another. One after the another. How one after the another? For example, here resistance R1 is connected to the end A. One end of the resistor connected to the terminal A. Other end is connected to the second resistor R, whose resistance is R2. Similarly, the second terminal of the resistor 2 is connected to the point C, which is the first terminal of the resistor, which resistance R3. And the last resistor R3, its second terminal is connected to the point D. So I can say that a potential difference is maintained between the point A and D because A is connected to the positive terminal or higher potential. At the same time, the point D is connected through a key to the negative terminal or lower potential of the cell. So children, here there is a single path for the flow of current. When the circuit is on, switch is on or the key is on, we are drawing the current. For example, we are drawing the current of I ampere from this circuit. So there is a single path. So the flow of current throughout the path will be equal because there is a single path. But here the resistances are different. I have taken here R1, R2, R3. So definitely there will be a potential differences. Current will be remain same in series connection, but potential will not be same. Why the potential will not be same? The reason is that here resistances are different. We know that from Ohm's law, V is equal to I R. In this case, the current is constant. How much current flowing through this resistor? With resistance R1, same current flowing through the R2, same current flowing through the R3. That means I can say that I is here constant. This I is here constant. That means the potential difference across its ends is directly proportional to resistance. So this potential difference is directly proportional to its resistance. Earlier we have studied from Ohm's law. So children, for example, VA is the potential difference between the points A and B. I can write, suppose V1 is equal to potential difference between A and B. Whenever current is flowing through that, resistances are different. Ultimately, the voltage will be different or potential difference will be different because I said that potential difference directly proportional to resistance. And earlier I have said that about the voltage drop. When current is flowing through the circuit, we observe there is a voltage drop inside this cell, that is due to presence of an electrolyte. So in this case, how much potential will be here? It will be here different, here will be different. Suppose here is potential difference is V1, here is V2, here is V3. So this V1 is more than V2, it is more than V3 because when the current is flowing, it is flowing from the end A to D. So it is passing through different resistances. So there will be a voltage drop. So how much voltage here? Here it will not be same voltage. If it is V1, it is V2 and V3, I can say that this V1 greater than V2 greater than V3. That means the potential difference, the last resistance will be less than the potential difference from its previous resistances. So that's why I have written V1 greater than V2 greater than V3. So far as series connection is concerned, I said that the potential difference will be divided among the resistors. If it is V1, this one V2, this one is the V3. I have written V1, V2, V3. But I have mentioned the current I. That means same current is flowing through it. but the potential difference across different resistors will be different. So one thing I can say that you have to remember that in series connection, potential difference is directly proportional to resistance, and here the total potential I can write it is equal to potential at the point A minus potential at the point D, because the terminals A is connected with the higher potential, terminal D is connected with the lower potential through a key. Now the key is closed, circuit is in working condition. Now the potential differences between the point A and D will be VA minus VD. So I said that you have to remember one thing, in case of a series connection, the total potential difference is equal to sum of the individual potential difference. I can say that this V equal to V1 plus V2 plus V3. Okay, so let us start to calculate the equivalent resistance in series. Equivalent resistance in series. We have to calculate equivalent resistance in series. So I said that V is equal to V1 plus V2 plus V3. So already I said that since current is passing through the same circuit, through the same path, it is constant, it will not divide. Then which one will be divided? Only potential difference will be divided. So I can write that V1 is equal to I upon R1, because from Ohm's law we know that V equal to V equal to I R. So in this case I can say that V1 is equal to IR1, V2 is equal to IR2, V3 is equal to IR3. Clear? Because we know that voltage is the product of a current and resistance. So if here is the voltage V1, current is I, resistance R1, V1 is equal to IR1, V2 is equal to IR2, V3 is equal to IR3. Suppose now the circuit is in series connection. Let RS be the equivalent resistance in series. RS is the equivalent resistance in series. Then if V is the potential difference, between the point A and D, so I can write that V is equal to IRS. RS is the resistance when the resistors connected in series. V is the potential difference across the ends between the point A and D. So I have written V equal to IRS. Before that I said that V is equal to V1 plus V2 plus V3 if these three resistors are connected. So now I can say that in place of V I can write IRS is equal to IR1 plus IR2 plus IR3. This is if I take common IR1 plus R2 plus R3, implies that resistance in series is equal to R1 plus R2 plus R3. That means if the resistances are connected in series, the equivalent resistance is equal to sum of the individual resistances. Suppose in general term I can write that if a number of resistors are connected in series, then I can say that and all are equal. Suppose this R1 equal to R2 equal to R3 like equal to Rn, then I can write that resistance in series is equal to n times of R. In case of a general term, I can express like this. So this is about the series connection. Let us move towards the parallel connections. Resistors in parallel. So we discuss now about how the resistors are connected in parallel. Suppose this is common point A, this is the common point B. This is the positive terminal of the cell, negative terminal. This is the key. Okay. Now suppose the amount of current drawn from this circuit is I. The direction of current all the time from higher potential to lower potential. So here the current is I1, here this is I2, here this is I3. The resistors, suppose this is R1, R2, this is R3. Listen carefully. In parallel connection means all the first terminals of the resistors are connected to a common point. At the same time, all the second terminals are connected to another common point at the point B. There is a potential differences between the point A and B. I said that is VA minus VB. But whenever we are drawing the current, in case of a parallel combination, when the current reaches at the point A, because it is moving from higher potential to direction lower potential according to conventional current. So when current reaches at the point A, it divides between the three resistors. Suppose the current through first one is I1, second one I2 and third one is I3. That means current is here divide among the resistors, but potential difference is same. Why? All the time it is the difference between A and B. So I written potential difference VA minus VB. All the resistors are connected. Its first terminal to one point, its second terminal to another common point. So there will be no difference in potential difference. Only there will be difference in current. So I can say that in case of parallel combination, I is equal to I1 plus I2 plus I3. Okay. So I retain I is equal to I1 plus I2 plus I3. So already you know that from Ohm's law, V is equal to I R, or I can write that I is equal to V by R. So if I is equal to V by R, I can say that I1 is equal to V by R1, I2 is equal to V by R2, I3 is equal to V by R3. Suppose here the current drawn from the cell is I ampere. So I can write that this I is equal to V by Rp. Here Rp stands for equivalent resistance when the resistors are connected in parallel. But I have mentioned here I is equal to I1 plus I2 plus I3. Then here I can say that V upon Rp is equal to V upon R1 plus V upon R2 plus V upon R3. Potential difference is constant between the points A and B because all are connected to the point A and B. Only current is different. So I can write like this: V of 1 by R1 plus 1 by R2 plus 1 by R3. This V we cancel, implies that 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. That means the reciprocal of the resistances in parallel is equal to sum of the reciprocals of the resistance in individual. That means reciprocal of the resistance in parallel is equal to sum of the reciprocal of the resistances, individual resistances. So suppose there are two resistors are there. For example, you think there are two resistors are there. So if two resistors R1 and R2 are connected in parallel, so I can say that R1 plus 1 upon R2. If I take the LCM, implies that resistance in parallel R1 R2 upon R1 plus R2. If two resistances are connected in series, or if two resistors are connected in series and their corresponding resistances are R1 and R2, then this will be the equivalent resistance when they are connected in parallel. So this is about the series and parallel. And one more connection is there. I said it may be in both series and parallel. Both series and parallel. Means series and parallel. Series as well as parallel. Then we have to connect it like this. Different ways are there. For example, these two I have connected in parallel. After getting its equivalent resistance, I shall connect it with these resistors in series form. Then we can get the combined resistance. So according to our requirement, according to our desire, we can connect a number of our resistors in series as well as parallels. See that, for example, here two resistors. This is 1 ohm, this is also 1 ohm, this is also another 1 ohm resistors. They are connected like this way. Then what will be its combined resistance? So these two are in parallel. So I can say that, just I said that this is R1 R2 upon R1 plus R2. Listen carefully. I said that 1 by Rp is equal to 1 by R1 plus 1 by R2. So this is R1 R2 R1 plus R2, okay, or this Rp is equal to R1, this Rp, okay, Rp is equal to R1 R2 upon R1 plus R2, same formula I am using. So this is equal to 1 into 1 upon 1 plus 1, okay, that means we got 1 upon 2. So these two will combine with this one. Okay, that means Rp. This is, you think R1, you think this is R2. Okay, so this is R3. So this Rp plus R3, it is connected in series. That means this is half plus 1. This is 1.5 ohm. Okay. So I can say that suppose 3 resistors are there. Each resistance are 1 ohm. We have to connect it to get a resistance of 1.5 ohm. That means the 2 resistors we have to connect in parallel there, and again third one we have to connect with the series with this parallel combination. Like this way we can find our desired resistance. So there is series connection, there is parallel connection, and third connection I said both may be series and parallel. Both things you can find it. So if I draw a graph between this in IV graph, you will find that resistance equal to ratio of slope on IV graph. Resistance is equal to ratio of slope on IV graph. So if I take the I in y axis and V in x axis, then if it is parallel combination, you may get the graph like this. If this is series, this is parallel. So in this case, definitely you find the slope is more than slope in this case. Here the slope is more. That means the resistance will be less. In parallel, resistance will be more. Sorry, in parallel combination, resistance will be less, and in series combination, resistance will be more. And in this case, here in series, slope is less, but in case of parallel combination, slope is more. So children, this is all about the different combinations. According to our requirement, will combine whether series or parallel. So this is for this video. Next video, I shall prefer to go through numerical problems, which is very important from your exam point of view. So children, you have to study systematically. You have to, if you want to learn, you have to watch the video consistently, not one video. Okay, then you can get its result. So thank you children.